out the derivative function. Example 3. Estimate the derivative of the function at x equals -2, -1, 0, 1, and 2 for the function below. When we want to estimate the derivative of a function at a point, we're asking to approximate the slope of the tangent line at that point. So I've drawn in the 5 tangent lines that we're interested in trying to approximate the slopes of. Now, if I didn't have them already drawn in, I would take a ruler or a straight edge or use my best guess to try to visualize where that tangent line would be. So remember, tangent lines only touch at one point, and the point where they touch are the points we're interested in. So let's start by looking at the derivative of the function at -2. So at -2, my tangent line touches right here, and you can see it's sort of an orangish red color. So I'm trying to approximate the slope of that tangent line because it's the slope of the tangent line that will tell me what approximately the instantaneous rate of change is. In order to get the slope of a tangent line, I need 2 points on that line. If I have 2 points on the line, I can do the change in y over change in x to get the slope of that line. So remember, I'm no longer looking at points on the function when I'm approximating the derivative. I'm looking at the points on the tangent line. So I can pick any 2 points I want, but I'm going to try to pick them somewhat strategically. So here, this looks like -2, 4. And then down here, this bottom part of the tangent line looks like it goes through at -1, 0. Now again, I could pick any points on the tangent line. At the top of the line, it looks like -3, 8. I could pick something in between. I'm trying to pick numbers that are whole numbers to make my calculations a little bit straightforward. So again, I'm approximating the derivative at -2. And the derivative is the slope of the tangent line, which I'm going to calculate by doing change in y over change in x. So my change in y is going to be 4 minus 0. And then my change in x is going to be -2 minus -1. So on the top, I have 4. On the bottom, notice I have a minus a negative. So those are going to cancel, and I end up with -2 plus 1, which is -1. 4 divided by -1 is -4. So my approximation for the derivative at -2, which is the slope of the tangent line at -2, is -4. I'm expecting the slope to be negative because my tangent line is downward sloping. So this all seems to make sense with what I expected to happen. Let's go ahead and look at what happens at -1. At -1, my function is right about here. My tangent line touches. I've drawn in a blue tangent line to look at what's happening at -1. And again, I'm going to try to find 2 points that are on my line and use that to approximate the slope of the tangent line. So again, I'm going to try to pick these a little bit strategically. So this point right here where I actually touch the function looks like it's happening at -1, 1. So I go over -1, and then I'm about halfway between 0 and 2 on the y-axis. And then I have to pick another point that I think is on this line. So I'm looking over here, and this right here looks like it's at the point 0, -1. So both of these points are on my blue line. And again, I don't have to use these points. I can use any 2 points on that blue line, but these ones seemed like they'd be easy to work with. So now I'm going to do the change in y over the change in x. So the change in y, I'm going to do 1 minus -1. Right? So those are my y values. There's my 1. There's my -1. So the change in y, now the change in x is going to be -1 minus 0. So -1 minus 0. So on the top, the minus and the negative cancel, giving me 2. And on the bottom, I just have -1. 2 divided by -1 is -2. So the slope of my tangent line at -1, or the instantaneous rate of change at -1, is -2. So now let's try the next one. The next one is at 0. So that's an interesting case here. I don't know if you can see, hopefully, that yellow line. But what's happening at 0, we have the point 0, 0. And then we also have pretty much any other point on the origin. So I'm going to use the same point over here, -1, 0, that I had used before. So if I do my change in y, I get 0 minus 0 over the change in x. So the change in x is going to be 0 minus -1. We have to be careful that we're not dividing by 0, but here we're not. We have 0 divided by 1, and 0 divided by 1 is 0. So if you have a fraction and you end up with 0 in the numerator, that means that the whole thing is 0. That's okay. We only have to be concerned if 0 is in the denominator. So that means the slope of my tangent line at 0 is 0. And that makes sense because if you can visualize that line, or if you can see it in that light yellow color, you can see that it's a horizontal line. And we know that horizontal lines have a slope of 0. So we'll continue working our way to the right. So the next point that we're interested in is going to be the point at +1. So at +1, we're touching right about here. And again, we want to find 2 points on this line. We can see that the point 0, -1 is on this line as well, because they both cross through at the same point. And then we'll use the point 1, 1, because here when x was 1, it looks like y was also 1. So to approximate the derivative at 1, we're going to do the change in y. So we're going to do 1 minus -1 divided by the change in x, 1 minus 0. Again, if you subtract the negative, those cancel. So we end up with 2 divided by 1, which is +2. So we're expecting a positively sloped line because that blue line looks like it's going in the upward direction. So we were expecting a positive result. So that's good. And then finally, we want to approximate the derivative at 2. So at 2, we're right about here. We're picking 2 points on this line. So again, we'll pick 2, 4. That's 1 point. And then we'll go ahead up here and we'll pick 3, 8, which is sort of where I stopped drawing this line. But the tangent lines go on forever and ever. So again, you can pick any 2 points on the tangent line. Just choose ones that are easy to work with or the easiest for you to work with. So here, change in y over change in x, the change in y is 8 minus 4. And then the change in x is going to be 3 minus 2. So on the top we get 4, on the bottom we get 1. And so we get that the derivative at 2 has a slope of 4. So if we want to approximate the derivative at any point on a graph, we need to draw on the tangent line, find 2 points on that line, and approximate the slope by doing change in y over change in x. And that's how we approximate the derivative at various points on a function using a graph. Example 4. Find the intervals where the function below is increasing and decreasing. Determine if there is a relationship between where the function is increasing and decreasing and the sign of the first derivative. So our function is going to be increasing when the y values are going up from left to right. So the first interval where that's happening looks like it goes from -2 until 0. So we're going to be increasing from -2 until 0. And then it looks like again from 3 until about 6.25 approximately. Notice that 6.5 is here, so it's about halfway between 6 and 6.5. And then we're going to be decreasing when our y values are going in the downward direction. So that's going to happen from 0 until 3. and then again from 6.25 till about 8. It looks like the function is going to end around 8. So those are the intervals where we're increasing and decreasing. And the question wants us to look at whether or not that's related to the sign of the first derivative. So the sign means we're looking at things like positive, negative, and 0. So there's a difference between when things are increasing and decreasing and when they're positive and negative. So here in this original function, if we just look at the picture, this entire graph is positive because it's above the x-axis. However, there are places where it's increasing and places where it's decreasing. So positive and negative evaluates when we're above and below the x-axis, whereas increasing and decreasing describes what the function is doing as you move from left to right. However, we're trying to look at the sign of the first derivative, which means we need to start looking at some tangent lines. So let's look at the intervals where we're increasing. If we go ahead and draw in a bunch of tangent lines wherever we're increasing, we can look to see if there's any patterns here. So I'm just picking some places and I'm drawing them in. So when I look at these tangent lines and I'm trying to determine, do they have a positive slope, a negative slope, or a 0 slope, I start to notice that all of these little tangent lines have a positive slope. And that's not a coincidence. Turns out when your function is increasing, the first derivative is always going to be positive in those places. We can do something similar for our function here wherever we're decreasing. So if we draw in a bunch of tangent lines wherever we're decreasing, which is over here and over here, what we're going to notice is that all of those tangent lines are negatively sloped. Negative, 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 negative. So that means that the first derivative is going to be negative whenever our function is decreasing. And what's also interesting to point out is that right where we turn around from increasing to decreasing, those are exactly the points where our slope is 0. So right at 0, right at x equals 3, and at x equals 6.25, the slopes of those tangent lines are going to be 0. And we said that those places where we change from increasing to decreasing or decreasing to increasing, we call those points constant. So when the function is constant, the derivative is 0. So again, if our function's increasing, any derivative that we calculate on that interval, we expect to be positive. If our function's decreasing, any derivative we calculate on that interval, we expect to be negative. And if we're at the point where we turn around from increasing to decreasing or decreasing to increasing, we're expecting our derivative to be 0. So this brings up our first set of rules about the relationship graphically between the original function and the first derivative. These are going to become really important, and we're going to build upon these as we look at different types of functions. So what we said is that if f of x is increasing on an interval, then f of x is positive on that interval. If f of x is decreasing on an interval, we say the derivative is negative on that interval. And if f of x is constant, then we say that f of x is 0 on that interval. This is one of the most important sets of rules that we are going to look at to begin building our foundation of how functions behave graphically. So it's really important that we start to practice this and have a really good solid understanding about this relationship before we bring in new relationships. So let's look at an example. Example 5. Given the graph of f of x below, determine the intervals where the first derivative is positive, negative, and 0. So thinking about our rules, if we want to first decide where the first derivative is positive, we want to find the intervals where the original function is increasing. So whenever we're increasing, the first derivative is positive. So taking a look at this graph, it looks like I'm increasing from roughly, so we're going to be increasing from negative, let's say 1.4 until 0. So this part of the line right here, right, we're going to be increasing all right here. And then again, over here, from about 1.4 till about 2.5. So if my function is increasing, then my first derivative is positive, right? So that means any tangent line that I draw where I have those squiggly lines for increasing, the tangent line will be positively sloped, and the slope of that line will be some positive number. Now let's talk about where the first derivative is going to be negative. So again, the first derivative is going to be negative where the original function is decreasing. So here we can see that we're decreasing from roughly negative 2.5 until negative 1.4. So all right here. And again from 0 to 1.4. So on those intervals, any tangent line we draw is going to have a negative slope. So the first derivative is going to be negative wherever the original function was decreasing. So then finally, we're going to have a 0 slope wherever we change from increasing to decreasing. And we have this horizontal tangent lines. Looks like there's 3 of them here. And so the derivative will equal 0 at x equals negative 1.4, 0, and positive 1.4. Because those are the places we are going to have the horizontal tangent lines. Now, these rules that we're working with, they work in both directions. So if for some reason you knew that the first derivative was positive, that would tell you that the original function was increasing. If you knew that the first derivative was negative, that would tell you that the original function was decreasing. And if you knew that the first derivative was 0, that would tell you that the original function had a horizontal tangent line, or that it was constant.